So this topic is star to delta and delta to star transformation. First of all, we should understand what is the meaning of this star and what is the meaning of the delta and what is the need of this transformation. Okay. So delta, it is the old concept. You have heard the delta in different contexts earlier as well, in geography as well, and also in mathematics. In simple language, you can say that delta is nothing but a triangular shape. Okay. So what is the difference between the delta of the geography and delta of the mathematics and delta of the electrical engineering, or you can say what is the similarity between them? Similarity is that every of these concept is denoted by a triangular shape. Okay. So in but in the electrical engineering, this triangular shape which is denoted by delta is, firstly, it is the enclosed figure, and it is having the resistances in the branches. Okay. So as shown here. So next thing is the what is the need of this, and next is the star. So star is again the y point shape, y shape, and in this star you can denote by the capital Y as it is given. It is having four nodes as given the diagram. ABC nodes is given, and one is the common node which is connected by all these three branches. And in the mesh or the delta system, it is having three nodes. Okay. So we have observed few theorems: KCL, KVL, Maxwell circulating, and nodal equations, nodal theorem. And also in forthcoming classes, we will also learn few more theorems. So based on our convenience to handle the nodes, and based on our convenience to solve the closed loops, we can transform star to delta or delta to star. This is one thing. Second is the demand of the circuit. If the DC circuit is in a complicated position, and by doing some star to delta transformation or delta to star transformation, if some of the part of the circuit can be simplified, then again we go for this transformations. Okay. So first is how to perform delta to star transformation. Okay. So you can follow any book or you can follow same this notes, but you have to remember the end results, and it is better that you follow a particular one literature at a time, because for this transformations, if you follow more than one literature in star to delta transformation or delta to star formation, you are likely to get confused. Okay. So I will explain you using this, and what is the nomenclature defined here. So in the delta, the vertex of the triangle is ABC if we follow the clockwise arrangement, as you can see. Okay. Similarly, again in the star connection, the nodes, external nodes, we are not talking about the common node, We are talking about the external loads. It is given as A, B, C, and again these are following the cyclic or clockwise notation. Okay. So first thing first. Next is the resistances nomenclature. Resistances are given R1, R2, R3 again in clockwise notation, and RA, RB, RC in star connection again in clockwise notation. Okay. So this thing for it should be clear. That notation part should be clear. Now we will see how we will do the transformation. So now you focus on the next diagram which is given. So first of all, we will perform the delta to star transformation. So these two systems will be equivalent if the resistances measured between any pair of lines is same in both the systems when the third line is open. Okay. So these two resistance or the system of resistance should be equivalent and third line should be open. So what we will do, we will pick the A vertex and pull above the B and C vertex. Okay. So what will happen here? So when we are doing this, the R1 and R2, these two resistances are pulled above from R3. So these R1 and R2 are in series, and since it is having a, it is being disintegrated from R3, so it will be the series combination of R1 and R2 will be in the parallel arrangement with R3. Okay. Okay. For example, you can say that this is the first R1 and it is in series with R2, and since it is being pulled away and some R3 is here, so these series combination of R1 and R2 is in the parallel combination with the R3. Okay. So similarly, we will see the star arrangement. Here this A vertex is pulled and the third line is open. So here these B and C are in series and A is disintegrated from them. Okay. So now we have to calculate the RBC resistance in both the cases, in star and delta, and equate them. Okay. So first of all, we will take the delta case. So here R3 is in parallel with the R1 plus R2. So we can perform the parallel theorem. 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. Okay. So sorry. First of all, we will do R1 plus R2, and now this R1 plus R2 is in parallel with R3. So equivalent resistance will be 1 upon R3 plus 1 upon R1 plus R2. Okay. So when we take the parallel arrangement of this and equating with the equivalent, we will get the RBC for the delta case as shown here. Okay. And in case of star, the resistance between RBC is the series combination of RB plus RC. Okay. So now we can equate both these things. The equivalent, this RBC and this RBC, we can equate to get the desired results. Okay. So similar to this, so we will equate these things and name this equation as equation number 1. Okay. Similarly, we can take the B vertex out of the delta and C vertex out of the delta and perform the similar combinations and get the equation number 2 and 3. Okay. So we will now see, is there some relationship between these equations, or we can do something, keywords or something, so that we can remember easily and rearrange. So when we add equation number 1, 2 and 3, we will get 2 RA, 2 RB and 2 RC. Okay, isn't it?
Yes, sir.
And in RHS, what we will get? In RHS, we will get this R1 plus R3. Okay, and again R1 plus R3 is here. So we will get 2 R1 plus 2 R1 R3. Similarly, this R2 R3 is here and R2 R3 is here. So we will get 2 R2 R3. Okay, and R1 R2 is here and R1 R2 is here. So we will get 2 R1 R2. Okay, so in the LHS, we will have 2 RA plus RB plus R3, and in RHS we will have 2 R1 plus 2 R1 R2 plus 2 R1 R3 plus 2 R2 R3, and this 2 gets cut, so the denominator will remain same. Okay, denominator is not a problem. So this is the desired result, which will be labeled as equation number 4. Okay, is that clear to everyone?
Yes, sir.
Okay, so now we have to get the values of RA, RB and RC. Okay, so what we are doing here, we have started from the delta and we have to reach out at star, because this is, first of all, we were doing delta to star transformation. So we want RA, RB and RC. These RA, RB, RC values we want in terms of R1, R2, R3. Okay, this is our final result, or this is what we are going to achieve. Okay, so equation number 4 gives RA plus RB plus RC, and equation number 1 gives RB plus RC. So if we subtract equation number 4, equation number 1 is subtracted from 4, we will get RA, isn't it? So similarly, if we subtract equation number 2 from 4 and 3 from 4, we will get the values of RB and RC respectively. Okay, so now we will label these RA, RB and RC values as equation number 5, 6 and 7. Okay, so we have achieved the transformation of star from delta. We begin with R1, R2, R3s and assume some RA, RB, RC values of the star, and we have found the relationship between them. Okay, so these can be summarized as the equivalent star resistance connected to a terminal is the product of the two delta resistance connected to the same and divided by the sum of the all three delta resistances. Okay, so now we will do the reverse thing. Now we will do the star to delta transformation. Okay, so in the equation number 5, 6 and 7 we have the values of Ra, Rb and Rc. So what we will do, we will multiply these values and then add these values. Okay, what we are going to do, we are going to multiply equation 5 and 6, equation 6 and 7 and equation 7 and 5. Okay, so we will get Ra, Rb, Rb, Rc and Rc, Ra. Okay, so let us say we are multiplying R1, Ra and Rb. So if we multiply Ra, Rb, what we will get? R1, R2, R3 and R2 again. So R2 is having the two values, or you can say R2 square and R1, R3. Similarly, if we multiply Rb and Rc, we will get R1, R2, R3 and another R3. Okay, so this is the result which we have achieved from it. So this is the R1, R2 square, R3, R1, R3 square, R3. And in the denominator, it will be R1 plus R2 plus R3 whole square. So from above numerator, if we isolate R1, R2, R3, we will get the series combination of R1 plus R2 plus R3, and which will be cut from the denominator. Okay, this thing is clear up till now? Dipanshu, is this clear now? Now we want that star to delta transformation, which means that we are now having the values of Ra, Rb, Rc, and we have to get the corresponding values of R1, R2, R3 in terms of Ra, Rb and Rc. Okay, so how we are going to achieve that? Equation 8 is with us and equation number 5, 6, 7 is also with us. So what is the similarity between the equation number 8 and 5, 6, 7? First of all, the denominator component is same. This is one thing. And other thing is that in equation number 8, R1, R2, R3 is there. And in equation number 5, R1, R2 is there. So if we divide the equation number 8 from equation number 5, denominator get cancelled out and numerator R1, R2 also gets cancelled out. So we get the value of R3. Okay. So this LHS is clear. Now we will focus on RHS. So in the RHS part, RHS of equation number 5 and which is the LHS of equation number 8. So in the equation number 8, there is this series addition of resistances taken two at a time, which is Ra, Rb plus Rb, Rc plus RC, RA. And in the equation number 5, what we have? We had RA. So when we divide equation number 5 to equation number 8, 8 by 5, we get the value of R3 in terms of RA, RB, RC. Okay. Similarly, we can get the values of R1 and R2 also by performing the division of 8 by 6 and 8 by 7. Okay. So in this way, we can get the values of R1, R2, R3 in terms of RA, RB, RC. Okay, is that clear to everyone?